Hello guys, welcome to my channel Algorithm Avenue. In our previous video, I have introduced you to a new website that is called TensorFlow Playground. In this video, we'll be seeing forward propagation. I'll be explaining you the entire process of forward propagation with what is forward propagation and why forward propagation is done and the total mathematical calculation that is involved in forward propagation. Okay, first let's see what is forward propagation. The forward propagation is nothing but the propagation of input data, the propagation of input data from the input layer to the output layer via hidden layers by linear transformation is called forward propagation. Let me define it again. The propagation of input data, the propagation of data from the input layer. This is our input layer. Okay, this is our input layer. From input layer to the output layer. This is our output layer to the output layer via hidden layers. These are our hidden layers. These are our hidden layers. Via hidden layers by linear transformation is called forward propagation. I'll be explaining you the linear transformation in the further part of the video. Okay, now this is forward propagation. Why to study forward propagation is in understanding the backpropagation algorithm for means knowing the mathematical process, knowing the mathematical calculation of forward propagation is very much important in understanding the backward propagation. So that is why we learn forward propagation in detail. Okay, now to understand this forward propagation, let me take an example dataset. This is our example dataset, simple dataset that we have taken to understand this forward propagation. Okay, in this dataset we have the quality of cement, that is percentage of quality of the cement, that is 90%, and quality of the bricks, strength of the bricks, that is 88%, and the quality of the paint, that is 78%, and y is nothing but the strength of the house. If the y is 1, then it is said that the house is strong. If the y is 0, it is said that the house is weak. Okay, this is our example dataset which has three features, that is cement, that is x1, bricks, that is x2, paint, that is x3. These are our three input features and this is our output. Okay, this is our output. Now what we have done is we also taken an example neural network. This is an example neural network that I have assumed to explain you the forward propagation. Okay, now this is our input data, this is our input data, and this is our neural network. This is our neural network which has two hidden layers. This is our first hidden layer and this is our second hidden layer, and this is our output layer, and this is our three layered neural network. This is our three layered neural network. Okay, now let's before going into the intuition of forward propagation, let first what we have to do is we need to calculate the total number of trainable parameters in a neural network. Okay, before understanding any algorithm, when a neural network is given, first calculate total number of trainable parameters. Okay, now let's see how many trainable parameters are there in our neural network. This is just an assumption. This is just an assumption that I have taken. This is just a assumption neural network that I have taken to make you understand the forward propagation. Okay, now let's see how many trainable parameters are there in our neural network. First, let's start with the first layer. This is our first layer. From here to here, we have our first layer. Now, how many trainable parameters are there in between our first layer? Okay. Now, how do we determine the total number of features? We just do the multiplication between the input features and the connections of input features into this nodes. Okay, we just multiply these input features with these three nodes. Okay, how many nodes are there in the input layer, we multiply it with that. Okay, now how many input features we have? Three, right? Three into how many hidden units are there in our first hidden layer? Three. So 3 into 3, that is 9. Or if you feel this as difficult, now calculate each connection. Okay, how many connections we have, that many weights we'll have. Now from our first input feature, how many connections we have? This is our first connection, second and third. Okay, now corresponding to this input feature we have three connections. Now corresponding to this input feature we'll be having 1 1 1 3, total 6. Now corresponding to this input feature how many weights will be having? This is our first input and the first connection, second, third. Okay, totally how many connections we have? 9 connections. Or you can multiply this 3 into 3, this 3 into 3, 9. Okay, both the ways will work, but this is little bit easier way. Multiplication is little bit easier way. Okay, we'll be having total of 9 weights in this first layer. In this first layer we'll be having total of 9 weights. Now how many bias will be having? First bias, each node will be having a single bias. Okay, each node will be having a single bias. Similar to weights, we don't have each bias for each connection. Okay, each bias for each connection will be having a single bias for a single node. Now how many bias will be having in this first layer? 1 2 3 plus 3. Now we'll move on to the second layer. Okay, this is our second layer. Now how many weights will be having with corresponding to this second layer? 3 3. Okay, now first hidden layer we have 3 nodes, and in the second hidden layer we have 2 nodes. Now 3 into 2, 3 into 2, that is 6. 6. Now how many biases will be having in this second hidden layer? 2 bias plus 2. Now we'll be moving on to the third layer. This is our third layer. How many weights we have? 2 into 1. 2 into 1, that is 2. Plus how many bias we have in our third layer? 1 plus 1. Okay, these are our total number of trainable parameters corresponding to this neural network. Okay, this is our assumed neural network. This is our assumed neural network. You can take any neural network and do this for propagation. Okay, this is just our assumed neural network, and corresponding to this we have these many number of parameters, these many number of trainable parameters. Total how much it corresponds to? 9 plus 3, 12, 18, 20, 23. We have total of 23 trainable parameters corresponding to this neural network. Okay, now what happens to this trainable parameters is when forward propagation is done, an output y hat is predicted, right? In our previous videos we already discussed that in this way forward propagation is done and we calculate our y hat predicted output. Now what happens is the true output, we subtract true output and predicted output, y minus y hat, means that is called loss. In this way loss is calculated, and if the loss is greater, to reduce this loss we go with the backward propagation, back propagation. In this way again these trainable parameters are adjusted, and again you go with the forward propagation, and again loss is calculated, again backward propagation is done. In the process of backward propagation you adjust these trainable parameters. These trainable parameters are again readjusted, and again loss is calculated. How many times this is done is until this loss is reduced, until you reach the global minima. This entire process continuously takes place. Okay, now after altering this out, after knowing this total number of trainable parameters, we will be again going with another assumption that each node is having an activation function, and that activation function is sigmoid activation function. Okay, our first assumption was taking this data, second assumption is taking this neural network, and third assumption is the activation function used in this entire neural network is sigmoid activation function. Okay, sigmoid activation function. Now let's see what is linear transformation. In defining the forward propagation I have said that linear transformation is applied on the input data. But how linear transformation is applied is linear transformation is equal to weight transpose into x plus bias. Okay, this is linear transformation formula. We transpose the weight matrix and multiply it with the input matrix and then add bias matrix to it. Okay, in this way linear transformation is done on the input data. weight transpose matrix is multiplied with input matrix and it is added to bias matrix. Okay, in this way linear transformation is done on the input data. In our next section of the video we'll be mathematically seeing how each node, okay, how each node how linear transformation is done in each node. Okay, how linear transformation is done in each node. Okay, and the output y hat is predicted. Okay, in this okay, in this section we have assumed the entire we have built an entire setup, and in the next section of the video in the next section of the video we'll be seeing the mathematical procedure, how linear transformation is applied on the input data and output y hat is predicted. In our previous section of the video, we have entirely built and setup to understand the forward propagation mathematically. Okay, now let's mathematically understand how we do a forward propagation in in a neural network. Okay, this is an reference. This is a reference neural network that we have taken. Previously, I have drawn it over here. Please note that neural network down. Okay, this is our reference structure. Now, by considering this reference structure, we are going to mathematically prove that output of this neural network is O31. Output of this neural network is O31. Okay. Now let's start with the linear transformation corresponding to the layer 1. Now, what is the formula for linear transformation? That is weight transpose into x plus bias. Okay, this is our linear transformation formula that I have told you in the previous section of the video. Now, basing on this, we will be determining the each layer's output basing on this formula. Now corresponding to the layer 1, first we'll be discussing corresponding to the layer 1. Now corresponding to the layer 1, we have three inputs: x11, x2, x1, x2 and x3. These are the corresponding three inputs to this neural network, to this our first layer. Okay, these are corresponding inputs to our first layer. Now what we have to do is we have to first determine our weight matrix. Now we have to determine our weight matrix. When you have seen our video on notation of the multi-layer perceptron, I have explained you how to denote each connections weight. I have told you how to determine each connections weight, right? Now basing on that we are going to build an weight transpose matrix for our first layer. Okay, now how to determine this weight transpose matrix is, now corresponding to this first feature we have three outputs. So corresponding to the first input feature we have three connections, right? For each connection we will be having a weight. Now this first features weights will be our first row. Okay, now w111, sorry, w111 plus, sorry, w111, w121, w131. This is our first row corresponding to this input. Now our second row will be corresponding to this second input feature. Okay, now with corresponding to second input feature we have three weights. Now we will be writing those three weights over here: w211, w221, w231. Now our third row will be corresponding to this x3 input features three weights. Okay, that is w311, w321 and w331. Okay, in this way we have built our input matrix. Now this transpose determines that when transpose operation is applied on the matrix, the rows becomes columns and columns becomes rows. Okay, this is the transpose operation in matrices. Now this is size of the matrix is 3 cross 3. Now to this in weight transpose matrix we are multiplying our input matrix. What is our input matrix over here? That is x1, x2 and x3. This is our inputs to our first layer, right? Okay, as we are determining the first layer output, our inputs will be x1, x2, x3. and corresponding to x1, x2, x3 features, we'll be taking corresponding weights. Okay, corresponding weights. Now to this we'll be adding biases. What will be our biases? What are our first layer's biases? We have in our first layer we have three hidden units. Corresponding to these three hidden units, we'll be having three biases. That will be b11, b12 and b13. These are our biases. Okay, in this way we are applying linear transformation on our layer 1. Now the size of the input will be 3 cross 1. Now the bias size will be 3 cross 1. Now, our next step will be applying the transpose operation on our weight matrix. Now, when we apply the transpose to our weight matrix, our rows becomes columns and columns becomes rows. Okay. Now, as this is our first row, our first row becomes our first column. So W111, W121, and W131. Now our second row will become our second column. That is W211, W221, and W231. Now our third row will become our third column. That is W311, W321, and W331. Now size of this will be 3 cross 3. Size of this will be 3 cross 3. Now to this transposed matrix will be multiplying our input matrix, that is x1, x2, and x3. Now to this matrix we'll be adding our bias matrix, that is b1, b11, b12, b12, and b13. The size will be 3 cross 1 and 3 cross 1. Now first let us multiply both these matrices. For matrix multiplication, this both must be same. This both must be same for the matrix multiplication, and resultant matrix size will be this. Okay. For any two matrices to get multiplied, these two must be same, and the resultant matrix will be this cross this. Okay. Now first let's multiply this X matrix, that is input matrix, to our weight matrix. Now this column will be multiplied to this row. Okay, this column will be first multiplied to this row, that is w111 x1 plus w211 x2 plus w311 into x3. Okay, now similarly for to determine the second row, this column will be multiplied with this row, that is w121 into x1 plus w221 into x2 plus w sorry 321 into x3. Okay, now this column will be multiplied with this row, that is w131 into x1 plus w231 into x2 plus w331 into x3. Now what is the resultant size? Of this matrix multiplication? That is, we have 3 rows and 1 column, so it will be 3 cross 1, and bias will be added to this, that is b11, b12, and b13, and this size is also 3 cross 1. When to perform matrix addition, the size of the two matrices must be same. While performing matrix addition, the size of the two matrices that you are adding must be same, then only matrix addition is possible. Now as we have a matrix, to this we need to add our bias matrix. Okay, now let's see how our bias matrix get added to this matrix. Sorry for the interruption. Let me clear up this. Okay, now let's see how matrix addition is done between both these matrices. Okay, now w111 into x1 plus, similarly I am writing this over here, nothing much, w211 into x2 plus W311 into X3. Now to this I'm adding bias. Okay, our first row will be added to our first row. Okay, our first row of the bias will be added to our first row of the weight matrix. So for this we'll be adding B11. Now similarly for the second row of this bias matrix will be added to the second row of this weight matrix. Now W121 into X1 plus W221 into X2 plus W321 into X3 plus bias B12. Now similarly, this third row of the bias will be added to this weight matrix. Now W131 into X1 plus W231 into X2 plus W331 into X3 plus bias B13. Now on this we apply activation function. On this we apply activation function. Okay, generally what happens in a node is, now first half of the node will do linear transformation, and the second half of the node will do will apply activation function on the linearly transformed data. Okay, now when we are talking about this node, when we are talking about this node, this half will perform linear transformation, and the other half will apply activation function to the linearly transformed data. Okay, similarly it happens to every node. Similarly it happens to the every node. As we are taking an entire layer, we will be applying, this is corresponding this. Okay, this row is corresponded to this node output, and this row is corresponded to this node output, and this row is corresponded to this row output. Okay, now on this linear transformation data we apply activation function, that is sigmoid activation function, and our corresponding outputs will be what generally, while I am explaining about the multi-layer perceptron notation, what will be the, I have also explained you the outputs of each node, outputs of the each node in the first layer, that is O11, O11, O12 and O13. These are the outputs of the first layer. These are the outputs of the first layer when we apply linear transformation and activation functions on the input data. Okay, these are our first layer outputs. Now this first layer outputs will become inputs to the next layer. Okay, now we'll be seeing that in the next section. In the previous section of the video, I have told you how linear transformation is applied in the first layer of our neural network. Now let's see how linear transformation is applied on the second layer of the neural network. But in our first layer of the neural network, the inputs came from our original dataset. Inputs came from our original dataset, that are our x1, x2 and x3 features. But when it comes to second layer, the inputs to our second layer will be layer 1 outputs. Okay, the inputs to our second layer will be layer 1 outputs. Now we already know the input matrix, right? When we are saying the inputs to our second layer are layer 1 outputs, then we have already know that we already calculated the layer 1 outputs, that is O11 and O12 and O13. Okay, these are our layer 1 outputs, which are inputs to the layer 2. Now we need to determine the corresponding weight matrix to our layer 2. Now when it comes to layer 2, we have two nodes, right? Two hidden units, right? Now to this two hidden units we'll be having 3 cross 2, total of 6 weights. Now how we denote those 6 weights is corresponding to this node in the first layer, and for these connections we'll be having 2 weights. Now the second hidden unit will have 2 connections, and third hidden unit will have 2 connections. Now for this corresponding weights notation will be W from our first node to first node, that is W2. As we are taking a second layer, K value is 2. So W11, first node to first node. Similarly, first node to second node, W2, 1, 2. Now when it comes to second node, W2, 1, 2 and W2 2 and 2. Now when it comes to third node, we have two connections. Similarly, though that will be 3 1 1 2 and 3 2, sorry, 3 2 2. Okay, this is a corresponding weight matrix when it comes to second layer. Now the corresponding bias matrix will be, how many biases we have in our second layer? Two biases, right? So it will be B21 and B22. Okay, this is our bias matrix. Now the corresponding size will be rows into columns. How many rows we have over here? Three rows. How many columns we have? Two columns. Similarly, how many rows we have? Three rows, and columns is similarly to 3 cross 1. Okay, now for initial step to this will be transpose, matrix transpose. Now we need to transpose this matrix. Now in matrix transpose, the rows will become columns and columns will become rows. Okay, now this row, sorry, this column will become our first row, W112 and W212 and W312. Now this second column will become our second row, and W322. Now, what is our corresponding matrix size? How many rows we have? Two rows. And how many columns we have? Three. Okay, now our inputs, I'm writing as it is, that is 3 cross 1. Now to this we will be adding bias, that is B21 and B22, and the resultant size will be 3. Sorry, this is not 3 cross 1, this is just 2 cross 1, and it will be 2 cross 1. Okay, now first our initial step will be to multiply both these matrices. When matrix multiplication is possible? When both these are same, when both these parameters are same. Okay, now here we have 3 and 3, it is same, and the resultant matrix size will be 2 cross 1. Okay, our resultant matrix size will be 2 cross 1. This is basic matrix multiplication. Now let's multiply our matrix, both matrices. Now this column will be multiplied with this row. Okay, W112 and O11 plus W212 and O12 plus W312 and O13. Okay, now this column will be multiplied with this row, W122 and O11, W222 and O12 and W322 and O13. Okay, what is the resultant matrix size? We have two rows, right? We have two rows, that is 2 cross 1, and our bias will be B11 and B22, that is of 2 cross 1 size. Okay, when two matrices can be added is when both their sizes are same. When both the matrices sizes are same, then those two matrices can be added. Okay, now let's see the resultant matrix of both this matrix addition. Let me rub this. Sorry for the interruption. I'll quickly rub this out. Okay, now let us add both these matrices. As we have both these matrices size are same, these both matrices can be added. So W211 O11 plus W212 O12 and W312 O13 plus bias B11 plus bias B. This first row is added to this first row, weight matrix first row. Now similarly, W122 O11 plus W222 and O12 plus W322 and O13 plus bias B22 is added to this weight matrix. Okay, the resultant size is 2 cross 1. Now this first row, it is denoted by O21 and this second row is denoted by O22. Okay, the second row is denoted by O22. Generally, in our multi-layer perceptor notation video, the second layer's output means when we have two nodes in our second layer, each output will be OIJ, right? General notation is OIJ, right? OIJ, right? Now this first node is connected to this node. Okay, this first node, so it will be O1, so it will be O11. Okay, sorry, as it is say Oij is nothing but this layer number and this is the node number in that layer. Okay, so sorry for the wrong convenience. Okay, now this will be, as this is our second layer, as this is our second layer, I value will be 2 and j value will be 1. Okay, j value as it is in the first layer, as in the first node in that second layer, it will be 1. Now as it is the second node, as it is a second node in the second layer, it will be 2. Okay, in this way outputs are denoted, right? Okay, we have already studied the notation of multi-layer perceptron. Similarly, that I am writing over here, and this is our second layer output. Okay, this is our second layer output, means this is the second layer output. Sorry for this, we need to apply again activation function. When we apply this activation function, this is our second layer output. Okay, now this second layer output will become an input to the third layer, first, where we have started our journey, we have taken the inputs from the actual data set. Now from that we have taken the inputs to the second layer from the first layer. Now we will be taking the inputs to the third layer, that is output layer, from the second layer. Okay, this will become the inputs to the third layer. This will become the inputs to the third layer. Okay, in our next section of the video we'll be seeing how output is determined, how linear transformation is applied in the third layer. In our journey of forward propagation, we are currently over this. Okay, we are currently here in our third layer. We have already determined the outputs of the two layers by linear transformation. Similarly, we will be determining the output of the third layer by the linear transformation, but this time the input will be coming from our second layer. Okay, coming from our second layer. Okay, what is our second layer output? What is our second layer output? That is O21 and O22. Okay, this is our second layer output. Now what will the corresponding weight matrix that gets multiplied to this inputs is this. Okay, from the second layer this connection to the third layer, and from the second layer second node to this connection will be this connection corresponding weights will become our weight matrices that gets multiplied to this input matrix. Okay, now what will be this corresponding weights is W3. As we are working on third layer, K value will become 3 and I becomes 1 and J becomes 1. Similarly, W3 1 2. Okay, W3 1 2. Okay, sorry, W3 2 1 2 1 2 1 means from first node to first node, from second node to first node. Okay, we have already see the notation of these weights in our previous videos, so I am not explaining it again. It will be, the size will be 2 cross 1 and this size will be 2 cross 1, and the corresponding bias that gets added to this matrix multiplication will be B31. Okay, this will be B31 of size 1 cross 1. Okay, now we need to apply transpose. We need to do this weight matrix transpose. That will become W113 and W213 of size 1 cross 2. Okay, to this what will be multiplied is O11 and O22. Okay, O21 and O22 gets multiplied to this matrix of size 2 cross 1, and bias will be of size 1 cross 1. Okay, now when matrix multiplication is possible? When both these parameters are same. Yes, right, when both these parameters are same, then matrix multiplication is possible and the resultant will be this 1 cross 1. Okay, now let's do the matrix multiplication. 3 O21 plus W213 O22 and to this will be adding bias B31. Okay, now we will be adding this bias to this matrix of 1 cross 1. Okay, now we'll be adding both these matrices as we have similar sizes. Okay, as we have same size, we'll be adding both these matrices. Now, when we add these matrices, then the resultant matrix will be O21 plus 3 O22 plus bias B31. Okay, of resultant size 1 cross 1. Okay, now this entire matrix will be denoted by O31. Okay, we already discussed in our previous videos the notation of this node, the notation, the output notation of this node, right? As we have only single node in our output layer, the output of this node will be Oij. Oij is nothing but I is the layer number and j is our node number in that layer. As we have single node in our third layer, it will be 3 cross, that is layer number, and 1. So our final output will be O31 when activation function is applied. When activation function is applied, our output will be O31 of size 1 cross 1. Okay, this is the entire output. Uh, this output corresponds to the entire data. This output corresponds to the entire input data, and this is also called as predicted output y hat. This is also called as predicted output y hat. In this way, the entire flow of the entire flow of forward propagation is done, and finally we will be getting an output matrix, and we'll be getting an output matrix. As we have a single node, our matrix will be 1 cross 1. When we have multiple nodes, let's say 2 nodes, our matrix size will be 2 cross 1. Okay, in this way forward propagation is done in a neural network. What you will be doing is, you take an reference neural network, you take a neural network of your wish and apply linear transformation and do the forward propagation for each and every layer and note down the matrices, and you see that this output matrix, this output of this our final node is equal to output of your entire forward propagation. Okay, until then, go on doing the matrix multiplications, apply linear transformation, and see that your output is matching with the final neural network output. Okay. Our upcoming videos will be also having the same mathematical calculations, that is backward propagation. Let's say backward propagation will be having still in deeper mathematical calculations, and activation functions, loss functions will be having more and more mathematical calculations coming on the way. So this is only the basics that I have explained you in this video. So please try to practice this entire flow once, and you check that your output of this your calculated output is matched with the neural network output. Okay, now thank you guys for this for staying connected with me till now. I hope you like the video. If you like the video, please like, share and subscribe. Thank you.